if we go ahead and travel inside of the kidneys, there are tiny little tubes known as nephron. These nephrons are basic structural and functional unit of the kidneys. A lot of things happens in the nephrons. In order to understand better what's going on with the nephrons, first we must see the pressures that are involved in there and understand how we can regulate things and why is it so essential to regulate things. So here you have the kidneys. Inside of the kidneys, there are tiny little tubes, all right? And these are the nephrons. And again, the nephrons does a lot of filtration when the blood coming into the kidneys from renal arteries. And we wanted to take a look at these. And you need to review your anatomy for different parts of the nephron. Right now, we are looking at the importance of how and why do we need to regulate things to begin with. All right. So, giving you a little bit of introduction. Um, there are different forces that are operating. So, if you have, for instance, your Bowman capsule, all right, and portion of the nephron that is in this side. On this side, right over here, you have the glomerulus and afferent arteriole. So afferent arteriole coming in, and then this is the glomerulus. All right. So there is a force in here. Okay. In general, what is happening is blood, as it goes from the renal arteries, they need to get filtered in here. All the waste and all the excess water, excess ions, drugs, byproducts of drugs, toxins, and things like that, they need to get rid of. All right. So, but there is a force in here. This force that is operating in here ultimately is coming from the heart, right? So the heart contracts due to the systemic circulation. This blood is going to go through the renal arteries and to the kidneys, and then filtration is going to take place right over here. In other words, the small materials, waste, and all that stuff, they're going to pass through, and you go through the process of reabsorption and all that. But right now, we wanted to know about this rate right over here. Now, let's face it, if you don't have any regulation and the heart is beating so fast or the contraction is higher and so on, this force right over here is going to be a lot higher. This is going to have higher amount of force in here. Okay, so in other words, more of these and a lot of force is applying in here. So if they're going too fast in here, all right, that's a problem. Why is it a problem? Because it does not allow for reabsorption to take place. So the first process, so let's go ahead and take a look at three processes that is happening in here. All right, there's three processes happening. Process one is called filtration. Filtration happens based on the size only. In other words, smaller material pass through, large material can't. Process two is called tubular reabsorption. So in other words, the things that you need of, the things that you want, water, ions, things in that nature needs to get reabsorbed through the parts of the nephron. All right, and the process three is secretion. In other words, again, toxins, drugs, hydrogen ion, things like that nature, you don't really want it, so they need to exit through the nephrons, okay? So this is called a tubular secretion. There is three processes that is going on at this point in time. However, if you have this force to be too high, in other words, let's say heart contracts so fast, let's say the stroke volume is so high, whatever the case might be, then these substances on the filtrate, whatever passing in here, this is called filtrate. All right, they're not going to have enough time to get reabsorbed. They're going so fast. So we normally reabsorb about 65% of water right here on the very first part of the nephron, which is called the PCT. If they're going too fast, you might only absorb, let's say, 10%. Very soon you're going to get dehydrated and die because all of this is going part of the urine. Now your urine output is going to be way too much, having a lot of water and other stuff. Same thing goes with other things, glucose. If you don't have time to reabsorb the glucose, all the glucose end up in the urine. All the ions that you need, all the vitamins that you need, all the uh, things that you need to reclaim, they're down the drain. Okay, so you need to have a regulation. What about if the stroke volume is so low or the blood force coming over here from the heart is too low? Let's say the person's heart is not working properly, right? Then what happened is very, what happened is, you know, uh, one of the idea of filtration is to get rid of waste because in our blood there is a lot of waste in here. These are nitrogenous waste and such. So if you don't reabsorb and you don't secrete and you don't have enough force, guess what? Waste is going to build up in our blood, and that is also problematic. So for that reason, we need to adjust. When this force is low, we need to somehow bring the force up. And whenever there is a lower flow, we need to increase the flow and vice versa. So we need to adjust. In order to learn about the adjustment and so on, first we need to understand the forces that are in play. So one of the forces that is involved is called hydrostatic pressure. So let's go ahead and take a look at this uh, hydrostatic pressure. This is in glomerular capillary. So we are looking at it right over here. Now, normal capillaries is about maybe, uh, 20 to maximum 40 millimeter Hg. Average is about maybe 26 millimeter Hg. But this uh, force right over here is pretty high. It's negative 55 millimeter Hg. So the force in this capillary is extremely high. This is because, again, afferent arteriole, it has higher diameter. Efferent arteriole, they have lesser diameter, and therefore they can have a higher pressure in this case. All right. But they are equipped with fenestrated capillaries, so they can pass through and so on. So that's a primary force. 55 millimeter Hg is this primary force coming in. Basically, another way of saying hydrostatic pressure in the capillaries is glomerular blood pressure. So this is the blood pressure. If you somehow you could put your pressure gauge right over here, it will read around negative 55 millimeter Hg. So that's one of the forces in play. All right, that's the primary force causing this filtrate to keep going. But there are two opposing forces that we need to take a look at. All right, one of those opposing forces happen to be hydrostatic pressure in capsular space. All right, in capsular space. Well, what does that mean? Well, let's take a look. Here is the Bowman capsule. If you do not know what we are looking at, we are looking at the portion of the nephron, all right? And here is the glomerulus, and here is the blood is coming in. So this force that we say in here was 55 millimeter Hg, taking and filtering the substances in here. Now, this, however, is not an open area. There are resistant factors. As they come across of these walls, all right, there are resistant factors. Notice that the, uh, you know, Bowman capsule gets like really tight right over here. So the filtrate, the fluid, along with the solute, they come into a contact of these walls. All right, and these walls are resistance. It's about negative 55 millimeter Hg or 15 millimeter Hg is the opposing forces in this case. I don't know if you ever put in honey in a funnel. Here's the funnel. All right. If you put in honey, the honey is not just going to go right away. Right? It's going to take time for it. So maybe a little bit later on, you get here, a little bit later on, it gets here, and then pretty soon they're all gone. Well, why didn't the honey went all the way in? Because of the viscosity of the honey, and they come into a contact of these walls of the funnel, prevent it to just coming in. Versus if you had water, would just go in a lot quicker, perhaps. But it's still water also have those resistance factor too, because they come into contact of the walls, but due to the nature of the water and such, and it's less viscosity, they're not just gonna stay there that long. Oil is kind of like that. If you ever change the oil, it's kind of like that too. You pour it in, and then again, you have to wait a little bit until the oil is gone. This is due to the opposing resistant factor. This is called hydrostatic pressure in a capsular space. Well, where is the capsular space? Just right here. All right. So it's not an open space that they're not going to come into a contact. They're going to come into a contact of these walls right here, which is equivalent to about 15 millimeter Hg. So you got 55 going this way. The opposing force is 15. All right. Now, colloidosmotic pressure in the capillaries, in particular, there is glomerulus capillaries, and they pull some of the substances towards the protein in the blood. Let's take a look at that. And that is another opposing factor, and that would be 30 millimeter Hg. So let's dissect this a little bit further. You see, here you have the first part of a nephron that is called the Bowman's capsule or glomerular capsule. And over here you have the glomerulus capillaries. All right. So yes, water and so on can pass, but certain substances like RBCs, white blood cells, those things, they do not pass because these fenestrated capillaries only allow the smaller stuff like water, for example, to pass through. Water can pass through, right? But biggest stuff, there are also like proteins, they don't pass because it's bigger than these slits, right? So let's put in the proteins right over here. So these are proteins. Right? So there's a lot of proteins that they do not pass. So water that it passed, and remember this force right over here was a 55 millimeter Hg. The capsular force, when they come into a contact of this capsular wall, was 15 millimeter Hg, which is opposing that force, 55 and 15. This one is 30. So in other words, some of the water, they don't want to go, they want to come back. Why? Because it's pulling towards the solute, which happen to be, in this case, a lot of proteins that are accumulating in here. Eventually, these proteins is going to go back to the circulation. So they're not going to stay here, but while they're doing the filtrate, it's pulling some of the water back. But is any of the water going back? No, it's not. Why not? Because of this force is high. Because of this force is high. Because the pulling force is about 30 millimeter Hg. So when you add up 30 and 15, that gives you 45 millimeter Hg opposing force. But our primary force is 55. So 55 minus the 45 opposing the two opposing forces. What do we get? We get 10 millimeter Hg, which is called net filtration pressure. So that's how you calculate the net filtration pressure. Two opposing forces, you add them up, and then you subtract it by the major force, hydrostatic or blood pressure. In this case, in the capsular, in the glomerulus, and that would be giving us a total of net filtration pressure of 10 millimeter Hg, which is normal. This is a normal pressure. It's not too high and it's not too low. This is what you need to maintain. What if the net filtration pressure drops? If it drops, what is telling you either opposing pressure is too high or the hydrostatic pressure or the blood pressure is too low. Either way, you're going to get a lower number in here, and that is not good. Why not? Because remember, the whole idea in here is to get rid of the waste. If the pressure is too low, waste is going to build up. To understand this concept, think about that nobody's taking out your trash or the waste. You're putting it out once a week so they could come in and take it. Let's say there's a strike going on, or they don't have the money to pay them, and so on. Nobody's coming up picking up your trash, so the trash is going to pile up. Waste is kind of like trash; it's going to pile up. But the problem is you can't delay it until later. The body can reach toxicity and you're in serious trauma. On the other hand, if this force is too high or these two forces is too low, what will happen again is going to influence the net filtration pressure, and it's going to cause the net filtration pressure to be higher than normal. And if that's the case, that's not a good thing, because then the filtrate are going too fast. All right. And as a result of that, you don't have time to reabsorb the material, because remember, a lot of things that are passing, they need to be reabsorbed back into the blood. But if they're going too fast, it doesn't give us a chance to reabsorb this. All right. So all of those combined is important. Then you might ask, what about when we exercise? Isn't when we exercise this number is going to go high because our blood pressure is going up? Yes, it does. What about when you're resting? Well, this number is going to go down. Isn't it the net filtration pressure is going to get messed up? Yes, and that's why we are going to look at how we regulate things. So when your heart rate influences, when the contraction is different, the bottom line is you need to make adjustments so it won't affect you, right? So what is this net filtration pressure offer us then? Net filtration pressure of 10 millimeter Hg, which is normal, by the way, offers us to have a correct glomerular filtration rate known as a GFR. Glomerular filtration rate is about 120 to 125 milliliter per minute. Okay, so what does that mean? It means if you have a container right on this side, in 1 minute, you're going to collect all these filtrate that you're collecting is about 125 milliliter. That's what it means. All right. So you're collecting the urine, for example, all right, or whatever is passing, not yet urine, but whatever is passing in this case. All right. In 1 minute, you're supposed to have 120 to 125 liter of the filtrate. This is normal. If the GFR is too high or GFR is too low, then you are in trouble. Okay, you wanted to maintain this at this range. All right, you don't want it to be too low. If it's too low, toxicity build up. If it's too high, no time for reabsorption. You're losing a lot of valuable material. This could be glucose that you're losing. This could be ions, this could be bicarbonate, this could be vitamins, this could be, water. All of those are important. Okay. Anyways, so now you know how to do the net filtration pressure. Let's go ahead and talk a little bit about the GFR. So this is the same ideas in here. It's just showing you the two opposing forces and one primary forces and how you calculate the net filtration pressure. So go over it, make sure you understand how you calculate things, okay? All right, now we need to talk a little bit about regulation of glomerular filtration. So again, normal range is what we wanted to achieve. Now we got to do something. If it's going high, we got to bring it back down low. If it's low, we need to bring it back up and so on. So we got to maintain this in the kidneys. All right. So if the GFR is too high, your urine output is going to be too high. Why? Because you don't have time to reabsorb. If you're losing a lot of water through your urine, then you're losing the pressure because the volume is lower. Okay, and vice versa. If your GFR is too low, urine output will be too low, the pressure may be too high, and again causing problems. So the goal of extrinsic control, meaning that we need to maintain the systemic blood pressure. Maintaining the blood pressure is important. Sometimes people don't realize, but they have a very high blood pressure, and they wonder, oh, well, I have a high blood pressure. How come it's affecting my kidneys? This is exactly why, because the kidneys are related in this case. All right. So there are two type of regulation. One is called intrinsic control mechanism. The other one is called the extrinsic control mechanism. Intrinsic control mechanism is called a renal autoregulation. Again, the autoregulation means automatically is occurring, right? It's acting locally within the kidneys to maintain the GFR. Extrinsic control is something that happens outside. This could be, for example, nervous system or hormonal control or endocrine system that could maintain the blood pressure and so on. And again, can affect differently. It's not within the kidneys, it's outside of the kidneys. All right. So those are called extrinsic controls. All right. So two type of now we are concentrating on the intrinsic control mechanism. Two types of renal autoregulation you need to know. And during the section of the cardiovascular system, I told you we will look at it later, and this is the later time. So myogenic mechanism, myo means muscle, obviously. Myogenic mechanism is related to the smooth muscle of the arteries or arterioles that the diameter can increase or decrease. And as a result of that, it can influence the flow. Tubuloglomerular mechanism, another factor that we're going to take a look at. And these are, again, you're playing around with the diameter of the blood vessels, but before that happens, there is a detection of osmolarities going on. And as a result of that, you could either dilate or constrict the blood vessels. All right. So whenever we wanted to take a look at the GFR, I wanted you guys to think about the flow. All right. If the GFR is too high, that means there is a higher flow. You have to lower it to lower the GFR. If there is a low GFR, then you gotta probably increase the flow somehow. So think about the flow. All right. And here you have the Bowman capsule at this point in time, part of the nephron. And over here, we mentioned you have the glomerulus right over here, but here is the afferent arteriole that is important right here. And this, they have the smooth muscles in here. We remember we mentioned that there is a tunica media consists of a smooth muscle, and these smooth muscles are important in vasodilation and vasoconstriction. This is an important factor of myogenic mechanism and tubuloglomerular mechanism. All right, so let's go ahead and take a look at what is happening. First, let's just hypothetically say during exercise. All right. During exercise, your GFR is obviously is going to go high. Why the GFR is going to go high? Because of the fact that the force of contraction of the heart is greater. That's what we mentioned. So when there is a higher contraction of the heart, then this force would be higher. So therefore, the GFR is going too fast. We need to lower it. All right. So now we need to think about the flow. How can I reduce the flow? If I can reduce the flow coming into the glomerulus over here, then I could reduce the GFR. And that's what I wanted to do because right now the GFR is too high, all right, during exercise. Without any kind of regulation, if there is no regulation, obviously you will lose a lot of water. Pretty soon, what happens? Your water volume is going to be lower in your body. You're going to get dehydrated. Blood pressure is going to be low, you know, and again, all those problems. So what we need to do, we need to, uh, reduce the GFR so they don't travel so fast. That is our intention. All right. So these smooth muscles are important. So, for example, if the smooth muscles constrict, all right, now there are pressure sensors that can exert or feel the pressure on these. And the more pressure on here, the smaller the diameter will get. If you lower the diameter, all right, you're automatically lowering the flow. And by lowering the flow, you're lowering the GFR, and that's what you wanted to do during the exercise. During at rest is opposite. At rest, the GFR is too low because the heart is not working that hard, and so on. So now you have to do opposite. You got to do something to increase the flow. All right. So in this case, you need to do a vasodilation. Dilation. All right. So that way you're increasing the flow. And again, this goes back to the idea of uh, vasodilation and vasoconstriction. This one offers you more flow, and this one offers you less flow. All right. This diameter is important. All right. So more flow, that means more coming out. Okay. Lower flow, it means lower coming out. All right. So that's what happens. This is at rest, lower the GFR. We wanted to increase the GFR. Well, how do we do that? By increasing the flow, by vasodilation. Now you have less resistance to flow. So what that means is we need to increase the flow. When we increase the flow, the GFR will be increased and the mission will be accomplished. So a smooth muscle contracts, all right, when they are stretched. This is during high blood pressure, and as a result of that, constriction of the afferent arterioles occurs, and that would restrict the blood flow into the glomerulus. This is exactly what I just told you. All right, this is for adjusting. All right, this is for adjusting. So in other words, let's say that we are looking at exercise. Now there is a vasoconstriction going on. So I'm going to lower the diameter now, right here. Now the diameter got smaller. So if the diameter got smaller, what happens? You're reducing the flow. This happens. By reducing the flow, you're reducing the GFR that was initially too high. Things will get balanced. All right? At rest is opposite. When you don't put enough force on these walls, they get dilated. When they get dilated, opposite happens. Now you have more flow. Very simple. All right? So this is called a myogenic mechanism. And the reason why we left it in here, because it happens in the kidneys. All right. Now we go over tubuloglomerular mechanism. Tubuloglomerular mechanism. All right. So these are dependent on the macula densa cells. All right. And they respond to the osmolarity, in this case, filtrate of NaCl. Let's go ahead and take a look at these macula densa cells. All right. See what they are and so on. And we could go from there. I think this picture might be helpful for you. All right. So if you look at this nephron, all right, you could see the loop of Henle, and some of the nephrons, their afferent, ascending loop of Henle and DCT, they're coming very close to this part right over here. So you can see the macula densa cells right over here. So this is the part of the nephron as they're going up. That's the ascending loop of Henle. If inside of it there is a lot of solute in here, these cells, macula densa cells, they can detect. They can detect the amount of sodium chloride or solute. All right? And that is what they do. Now, as far as what happens after that, they can release vasoconstrictor chemicals. So again, when the GFR is too high, all right, in other words, material is just passing through this really quickly, all right, and this ascending loop of Henle normally is permeable to sodium chloride. That means sodium chloride can get reabsorbed into our blood, but because they're going so fast, they're not. All right, so they're remaining here. So that means that there is a lot of solute in here. They can detect that, right? And as a result of that, they can release vasoconstrictor chemicals, and vasoconstrictor chemicals is going to constrict this afferent arterioles. And once you constrict the afferent arteriole, exactly same thing is going to happen as a myogenic mechanism. In other words, they're going to reduce the flow, and as a result of that, you're going to reduce the GFR, and as a result of that, you're balancing things because the GFR was too high on this phenomenon. Opposite can happen as well. In other words, the GFR could be too low. If that's the case, then there will be a lot of sodium chloride absorption, and the osmolarity is not going to be as much in here. So I guess I have to, erase a lot of these and think about that. And therefore, there's going to be less of these available and less vasoconstrictive chemicals. So therefore, vasodilation is going to happen. So those are the two auto-regulation. What does that mean? That means automatically is going to happen. All right. If I'm going too fast for you, if you do not understand, this is where the weekend comes in. This is where the Friday comes in. This is where the outside time comes in. You could review the material over and over again. This material is not meant for me to tell you one time and you can get everything in one shot. Do not get frustrated. Do not get intimidated. Just slowly go by your pace. Go and draw these things like I do. Pause the videos. Look at it several times, at least 10 times, at least 10 times. All right. If you do that, you might get it in the second time. You might get it in fifth time. It really depends on your learning. You all can get these. All right. It's not complicated. It requires you to work on it and understand it. Now, what if you choose the other way? You try to memorize. Okay, I memorize this thing happens here, this thing happens there. Uh, all I could tell you, you're not going to do very well on the final exam. So the choice is yours. You could rely on looking things up and hoping that I will ask you some questions that you could get by, or your final exam is going to be even more understanding, just like the previous exam. All right. Some of you guys mentioned that you did a lot of work, but you don't know why you got them wrong, or you thought that you knew it, but it was confusing. All of those confusion comes for a reason. It's because you didn't understand the material. That's why. All right. You try to memorize, you try to, overlook it, and you thought you were comfortable, but you weren't. That's why. Okay. Anyways, that's the idea between for the uh, macula densa and also the intrinsic control mechanism, tuberoglomerular and also myogenic. We are done with pretty much that. Now we're going over the extrinsic control mechanism. Extrinsic control mechanism is related to the hormonal control. And one of the pathway or the physiology that you need to know is called renin-angiotensin mechanism. Renin-angiotensin mechanism. This is very, very important to understand that as well. All right. So there are juxtaglomerular cells or JG cells that they release renin. Okay, before I go on and take a look at this renin, let's see what happens. Now, these are granular cells. Let's go ahead and take a look at where they are located. Let's go ahead and erase these. Right. So notice that afferent arteriole, as you come across to the glomerulus, these are the granular cells. All right. And because they're right next to, next to glomerular complex, these are called the JG cells. Sometimes we refer to as JG cells. All right, so look, these cells right there, these cells. So these are special cells that they have endocrine activity. What that means is they can release their content. In this case, renin. All right. Now, what is the renin is going to be? Let's take a look. Okay. And another thing I wanted to tell you is now on, we're just going to refer these two as JG cells because it's easier. Rather than saying granular cells of the juxtaglomerular complex. These are next to the glomerulus, all right? So we call it JG cells. They release renin whenever the blood pressure is low. So again, there are sensors in here that they can detect the blood pressure. When the blood pressure is falling, let's say you donate the blood, the pressure will be low. Right? JG cells, they're going to produce renin. They're going to release renin. All right? So say, for example, these are the renin. Now what? Now this renin is going to be in the circulation. All right? And is going to do something. All right? Is going to convert angiotensinogen to angiotensin 1. So let's go back to what we discussed before, and that was I believe right here. So angiotensinogen with the help of renin is going to become another molecule. So think about angiotensinogen, that is plasma globulin. Say, for example, this is this shape. Hypothetically, now with the help of renin, you break it down. Now it becomes different molecules, and we call it angiotensin 1. So you pretty much, let's say, broke this part into another molecule. All right. Now, angiotensin 1 needs to get converted into angiotensin 2. And this is where you need an enzyme. And some of our blood vessels involved in the respiratory, uh, the pulmonaries, arteries, and such, they have this enzyme. This is angiotensin converting enzyme. Right now, we are looking at it as ACE. ACE is abbreviation for that. So what's going to happen again is going to break this into a smaller one. And again, I did one of the presentation talk about the angiotensin in the coronavirus too. So right over here is angiotensin 2. Angiotensin 2, all of this happens because of the low blood pressure, folks. Right? This renin, because you had low blood pressure and it was released by the JG cells. Now you convert one type of protein to another, and again, further is going to get converted. Okay, now what? Now, this angiotensin 2, it does a lot of different things. Now, remember what it happens. It happens when your blood pressure is too low. This is the key right here. So when the blood pressure is too low, obviously you want it to bring it back up. What is happening? Well, when the blood pressure is too low, guess what? The GFR is too low. We're going to get to that. All right? But also, waste is building up. Right? We need to speed things up. Right? We can't, if nobody's coming out to take out your trash, you got to order somebody else to come in to and take care of it. Otherwise, the waste is going to build up. Pretty soon, your home, your yard, your everywhere is going to be trash, and you don't know what to do. You can't function, just like cells can't function. All right, so keep that in mind. Blood pressure is too low, folks. Keep that in mind really well, because the whole idea is how do we make this up? All right, so let's go ahead and take a look at what is the angiotensin 2 does. Angiotensin 2 can travel to the blood and go to the brain. And the brain thirst center is going to get stimulated. If it's stimulating, I'm just going to put positive. The thirst center in the brain, obviously, you're going to become thirsty. When you're drinking water, all right, that by itself, you're increasing the volume. When you're increasing the volume, your blood pressure is going to go up. And that is going to serve the purpose because now your GFR is going to go up. All right. Again, think about the flow. More flow of blood is going to go to the kidneys. So that's one of the things that happens. All right. Another thing that happens, angiotensin 2 is a vasoconstrictor to begin with. All right. So it's going to constrict the blood vessels of our body. This is not near the glomerulus, folks. This is just like overall. So mean arterial pressure is going to increase in mean arterial pressure. Mean is the average. Pressure in the arteries, all right? If it's lower, then if you constrict it, what happens to the pressure when you constrict something? It will go up. And therefore, there is more flow towards the kidneys. So in order to understand that, think about the kidneys right over here, all right? And let's say this is a renal arteries. Maybe I shouldn't draw it like that because you might think it's ureter. So this is the renal arteries, okay? And let's just say hypothetically, you have a bucket of blood in here. What happens if you squeeze in here, right? Kind of like same thing as squeezing other areas and so on. So if you're squeezing other areas, other blood vessels, what happens? There's going to be more flow in here. And that's the idea behind it. All right. So increasing the MAP is going to increase the blood pressure and therefore is going to also increase the GFR. And that's what we want because during low blood pressure, you had the low GFR. All right. What now? Now is also vasoconstrictor, so it's going to constrict efferent arteriole. Where is the efferent arteriole? Let's go ahead and take a look at that. Efferent arteriole lies right after the glomerulus. So here you have an afferent arteriole, blood comes in, they get filtered in here, and then it leads through the efferent arteriole. Now, if we squeeze this, pretend that we are constricting that because of the angiotensin 2, and there are receptors in here. And what happens is you are constricting this now. Let's say now is this much. As you constrict it, this is a vasoconstrictor. All right. Now what? Now you could see as the blood, let me just grab this one. As the blood is coming in here, they're gonna have a hard time because there's a more resistance in here to go in here. So what happens? More of them want to go the other way. Imagine that you are driving in a 5-lane freeway. This is a 5-lane freeway, right? And there are open lanes. All of a sudden, you notice like at the intersection of the freeway, all right, where you're supposed to go, all right, there is a big, huge traffic because of the car crash. If you get stuck in that traffic, it's going to waste a lot of time. So you might as well exit. Maybe that will help you understand why the pressure is going to be in here. It's higher now because you are reducing this diameter right over here now is reduced. So pretend this is not there anymore, right? So this will take me some time to draw, but here is reducing. Now they don't want to go in here, all right? They want to go this way. And when they want to go this way, that increases the flow. The higher the flow, higher the GFR. The GFR was too low already. So that's how. Next, where the GFR is important. So far, 3 mechanisms increasing the MAP by vasoconstricting, the efferent arteriole. So now there's more flow, and also the influencing of the third center. The last two is the stimulation of aldosterone. I should put adrenal gland, and the stimulation of uh, posterior pituitary, and therefore ADH. All right. So those two is also a way that they can help out, but we gotta figure out how. Zoom recording. So earlier we discussed about the uh, the different parts of the nephron. We are looking at this right over here is a collecting duct uh, and the DCT. There are certain cells in here that they respond to the hormone. And what I like to do is go over just put a small portion of it on the next page and tell you what happens in these parts. And then we can go ahead and take a look at the role of angiotensin 2. So let's go to the next page. So if you have, let's say these are the cells of the nephron, and within the vicinity you have, uh, you know, peritubular capillaries, and the role of posterior pituitary, uh, let's say these hormones is traveling via the blood, as we discussed in a previous lecture. And then these are the target cells. Now, they have these receptors as they come into a contact. Is actually a G-link receptor. But what happens is cascades of events happens in there, and posterior pituitary release ADH. Antidiuretic hormone, another name for it is vasopressin. And what it does, it creates these water channels. These water channels are known as aquaporin. So if the filtrate uh, blood gets filtered in the nephrons, and what you get is a filtrate. And if they have water in the filtrate, water now can go through this channel and end up in the capillaries via osmosis, right? Via osmosis. Because outside of this tube, you have higher amount of solute. You'll see a reason why shortly, but basically, remember what we did earlier. What happened was you had all right. So what happened is the water, it can go in here. Now earlier we mentioned that you had low blood pressure, and as a result of that, you had low GFR because the flow was lower. Now with the help of angiotensin 2, uh, it stimulates posterior pituitary to release more aldosterone, more ADH. And as a result of that, more of these channels. And as a result of that, more water gets into the blood, it gets reabsorbed right here. So when the water goes in here, obviously the volume goes up, obviously the pressure goes up, obviously the GFR eventually will go up. That's it. That's how it works. Angiotensin 2 also stimulates the release of aldosterone from adrenal gland. Adrenal gland uh, release hormone known as aldosterone. So pretend these are the aldosterone. Again, they can go into the target cells uh, readily because these are the steroid hormones, so they don't need outside receptors. So they could just like boom, go into the target cells. All of those are the target cells, and it could cause the gene to turn on and do a process of transcription and translation. And the outcome, or the protein, which is chain of amino acid putting together, happen to be sodium potassium pumps. So you're making a lot of these sodium potassium pumps. or ATPase. So what happened is you pump in 3 sodium out and you bring in 2 potassium in. They do have some potassium channel that potassium can go out, or some potassium channel that they could end up in the filtrate and ultimately in the urine. But because it's 3 by 2, and some of the potassium is ending up in here, so there will be a lot of solute in here. When there is a lot of solute, this goes back to the process of osmosis. Then when the water comes in, and there's water channels available, and sometimes the water can go between the cells too on the other side. Regardless, what happens is you're getting more water reabsorption because they're going to go where the solute is. Where is the solute? Outside of this tube and inside of the capillary. So now the water is going to just go in and follow this solute. And the same thing happens when the water goes reabsorb more in the blood, volume gets higher, blood pressure goes back up, the GFR gets back up. So remember, we had low blood pressure and a low GFR at the beginning. Angiotensin 2, it might take some time. It's not as fast as autoregulation, all right? Because you need the hormones in order to act upon it. You need to, have all of those conversion in place. But that's 5 methods that we discuss how you can, help with the angiotensin to monitor and regulate the GFR. There is a last mechanism. So let's go ahead and take a look at effect of angiotensin 2. So we mentioned this already. That's increasing MAP. Stimulate reabsorption of the sodium. We already did that. This is the aldosterone, so we're done. Stimulate the hypothalamus to release ADH. Well, the hypothalamus is actually goes to the posterior pituitary and then it releases, so that's we're done. Controlling of the thirst center, so you're also getting thirsty. This, they put it on the 3. I like to put it separately, all right, because you're thirsty, you're drinking water, your water gets absorbed through your intestinal wall, and therefore that would be number 4, right? And number 5, constricting the efferent arteriole. We mentioned those already, all right? And causes the glomerular mesangial cells to contract and decrease the surface area available for filtration. Don't worry too much about that right now. Mesangial cells, you can see these are the mesangial cells right over here. All right, so again, this is an apparatus next to the glomerulus, obviously. All right, so when it says glomerular mesangial cells to contract, basically they're squeezing, right? So when they're squeezing, they reduce the surface area, and therefore there's going to be less chances for the filtration. Okay, um, so renin-angiotensin mechanism. Don't worry about the receptors. I'm not going to talk about that too much, but I told you, what it can do. I think that would be sufficient. Let's go to the 4th mechanism. So far we looked at myogenic mechanism. We looked at tubuloglomerular mechanism. These were the intrinsic control, happens automatically, part of the autoregulation. All right. So this was manipulation of the smooth muscles, was critical to sense the pressure changes. So in a way, you could think about like, you're holding on the hose and the hose has water running in it, and your eyes and ears are closed, and but your fingers is holding on that tube, so you're feeling the pressure. But here's the thing: when the pressure exerts on your finger or the tube, then What you wanted to do is squeeze it even lower, more. So therefore, less will come out. Okay, and that's the idea behind it. And vice versa if you want to have more come out. Tubular glomerular mechanism, they detect the osmolarity, as we mentioned. The more osmolarity in the tube, they will release more vasoconstricted chemicals. So vasoconstriction is going to happen, and opposite, vasodilation in case there are less solute inside. Hormonal mechanism, angiotensin mechanism. Again, I went over it again. That's what happens in terms of aldosterone, what happens in terms of the ADH and all that. And then we are in the last part, which is a neural control mechanism. Now, these two are part of extrinsic mechanism. Neural control mechanism overrides all other three. So this one takes the first prize, these after. All right. So you might be in a household living and you might be in charge or control of everything. Let's say the kids, they're going to come and say, oh, can we go to the Disneyland? They want something, but you're in charge. You're going to say no. Can we go out in a concert? No. Can we go out in a party? No. Everything is no these days, right? Right. So you are in charge of what goes down. In this case, everybody wants to do what they wanted to do, but you're taking a stand and you dictating what should be done. Hey, social distancing or whatever the case might be, places are closed, we can't go. All right. So let's go ahead and take a look at the neural control mechanism, and then we can have a better idea of what's going on. So in order to understand this, I want you guys to think that this is only in emergency situations, only when you are under sympathetic activity. Sympathetic activity, severe emergency. Let's take a look what is happening. First, I want to give you a scenario. By the way, neural control mechanism is a sympathetic system. That's what it is. Let's take a look. Let's say a person gets stabbed and he's losing blood. Obviously, your blood pressure is going to be lower because you're losing blood. Obviously, your GFR is going to be lower because the flow is low. Flow of blood going to the kidneys and glomerulus ultimately. And if that happens, we already mentioned, without any regulation, if the GFR is too low, waste is going to build up, and pretty soon you're going to have a renal failure. Bottom line is, our intuition, our logic tells us, oh, okay, well, we got out of regulation. We're going to bring up the pressure back up, increase the flow, and do that. Or perhaps maybe even in tubular glomerular mechanism, or perhaps maybe even in the angiotensin II mechanism by various ways, right? No. During the emergency cases, the GFR is actually going to get lower. Because remember, this system overrides the other one. The other ones are saying, let's go to here, let's go do that, let's go ahead and increase the rate. No. Sympathetic activity taking place, norepinephrine is releasing, and vasoconstriction is happening. And as a result of that, the GFR is even getting lower. Okay? So we know now that, if that continues, the person is going to have a kidney failure for sure. All right. But why is the reason for that? Why is the GFR they want it to be even lower? It's kind of like not a negative feedback, because a negative feedback is telling us that GFR is supposed to be going higher when it's low. Yes, eventually, yes, but not right now. Because there's a sympathetic going on, sympathetic activities going on. A person got stabbed and he's losing blood. So let's analyze. Doesn't matter where the person has got stabbed. Okay. Uh, Here you got brain. Here you got heart. Here you got kidney. All right. So here's the kidney. Here's the heart. Here's the brain. Right. All right. So these are pretty important organs. You need blood to the heart. You need blood to the brain. Yes, you need blood elsewhere too. But let's say that you have a certain amount of volume of blood in here, which is right now, you're losing the volume right now. You're losing volume of blood because the person got stabbed, right? So you have less volume inside right here because you're losing blood loss. So your volume is low, your blood pressure is low. Do you actually want it to bring in this blood pressure high going into the kidneys? Because if you do that, then what's going to happen? Remember, you have a set amount of blood and you have a blood loss. Then there will be less for heart and less for the brain. Yes, let's say that your kidneys is saved. What are you going to do if your brain is no longer working? That doesn't make sense. All right. Which one would you rather to lose? Your kidneys or your brain? Your heart or your kidneys? Which one? Pick one. You see, it's not logical to send and flow the blood towards the kidneys, because if you do that, yes, you will adjust this GFR for sure. But then cardiac arrest, a stroke, you're gonna die anyways, right? So that doesn't happen. In fact, opposite happens. Vasoconstriction, that means, hey, we don't want to send it to you. We are shunting it towards here. We are going it towards here. I don't know, certain households are like that. They have pressure problem. Let's say you're taking your shower, all right, but simultaneously, let's say washer and dryer is on. Let's say somebody's washing the dishes. Let's say somebody's, watering the plants. Let's say somebody is washing the car outside. Everybody using the water at the same time. You open up the faucet, you notice that shower pressure is not much. Why? Because it's going elsewhere. Okay, so this is similar. If it's not going in here, it's going to go somewhere else and directing it somewhere else, and that's what you want, right? So but at one point in time you yell out loud, hey, I'm taking my shower, please turn off your water, or don't water the plants now, or whatever the case might be, and then you realize your shower is going to work fine after they shut off the water. And that's exactly what is happening. So the GFR, it does need to get adjusted. All right. So for that, probably you need a IV. You need an IV sending to the, maybe a paramedics comes in and give the fluid to this person. By increasing the fluid, you're increasing the blood pressure. And by increasing the blood pressure, you're adjusting the GFR that way. Again, this was emergency situation, but it overrides all other systems, because if you save the kidney, it doesn't make sense to have more blood for the kidneys and not for the brain and the heart. And physiologically, that's what happens and makes sense to what happens.